Hello, I am Zeinab Ganjei. I will present our work titled Verifying Safety of Parameterized Herd-of Algorithms. This is a joint work with Ahmed, Rezine, Petru, Eles, and Zebo Peng from Linköping University. Herd-of model is a uniform computational model for fault-tolerant distributed systems based only on transmission faults. Computations in this model evolve in rounds, and the model first handled only benign faults, being static or dynamic, permanent or transient, but was later extended to capture corruption faults. It is used to model many consensus algorithms like PAXs. Algorithms in the herd-of model have a common structure. Each algorithm consists of several rounds. In each round, there is one transition. And in each transition, a process first sends its local values, then it receives messages from others and stores them in a delta set called herd-of multiset. Herd-of is a multiset because of the possibility of occurrences, possibility of repetitions of the same message. Then after the sending and receiving steps, the processes execute guarded commands. There are several guarded commands provided. Each process executes the one whose guard is satisfied. The guards are formulas in terms of cardinality of herd-of multisets. We will see a motivating example. This is an algorithm called one-third rule, and it's a consensus algorithm introduced by the herd-of model. So in the beginning, the processes initialize some of their local variables. For example, here, they initialize their variable called res, which stores the result of the consensus. They have another variable called x, which will have an arbitrary value in the domain. We assume in our work, we require in our work that the domains are finite, but their size doesn't matter. Then in each round, there is just one transition that all the processes will execute. First, the processes send their X, then there is an implicit receive step in which they store the received messages in the herd-of multiset. Then there are several guarded commands provided. Guards are predicates based on the cardinality of herd-of. For example, you see the last one says if the cardinality of herd-of is lower than the threshold, then don't do anything. Or the one before that is saying if the number of occurrences of message 1 in the herd-of is larger than the threshold, then update both x by 1 and decide on 1. We take these algorithms in the herd-of model and we can verify safety properties for them. I should mention that we do not verify liveness for these algorithms. Safety properties for consensus protocols can be as follows. Agreement, which means if processes decide, they decide on the same value. Validity, which means if processes decide, they decide an initial value of some process. And last but not least, irrevocability means a process does not revoke its decision. We have several challenges ahead of us. First one is that some of the messages might get corrupted or lost. We don't know how many are so. The second one is that the number of processes is not bounded because we want to do parameterized verification. We want to verify correctness irrespective of the number of processes that execute the algorithm. So we will have an infinite state space that we need to traverse. We see in the coming slides how we tackle these two issues. Our contributions are as follows. We present a sound, but in general, incomplete procedure that terminates for parameterized verification of herd-of algorithms. We do that in the presence of lossy or corrupt communication. And in our verification, we use a symbolic representation based on cardinality constraints on multisets. We have implemented our work in a prototype and have done preliminary experiments with correct and buggy examples. Here we see how we model the configurations of the system. For the one-third rule algorithm that we saw, a sample configuration can be like this. So it's a tuple in which first comes the round number. Then we have a multiset of all the participating, all the participating processes. So here we have, for example, only two processes, different colors, model different valuations. Valuations are simply mapping from local values of the processes to their values. And then for each process, we also need to consider its head of multiset. A configuration can have a multiset of concrete processes. So we can have repetition of, for example, the green process here. Now the semantics of the transitions is as follows. For a configuration C that takes transition TR, we will end up in a configuration C prime whose round number is a round of C plus 1 and who has exactly the same number of processes as configuration C, and its processes are based on the guarded command which is taken by the processes in C. So there is a mapping from all the processes in C to the guarded commands that they take, and this will result in processes in configuration C prime. So we will require a symbolic representation that we call it a constraint, and the constraint actually denotes a possibly infinite set of configurations. Because the number of configurations is infinite, we need to group them in sets and consider each set at a time instead of looking at very concrete configurations, which are infinitely many. A sample constraint for the one-third rule algorithm is as follows. First, we have a control location, which is the round number modulo number of transitions. Then we have a predicate, which we call it global condition, which is a Pressburger formula, and has and its free variables are, first of all, n, which captures the number of processes and is a parameter, and the rest are variables that integer variables that capture the occurrences of different values of the variables among all the threads. For example, this integer variable captures the number of processes whose x is equal to 0. So GL is basically saying that more than 1/3 of the processes have their x being equal to 0. Besides these two parts, being control location and global condition, we have a set, this time, a set of process groups. Each process group is represented by evaluations. There can be one or more processes in each process group. So you see that here we do not represent processes concretely by the heard of. We just represent a group of them, and we get the summary of all the heard ofs, and a global condition basically intuitively shows a summary of all the heard ofs that can happen in this constraint. Now we need to define our denotation relation. So a configuration C is said to be denoted by constant phi if, first of all, their round number in C is compatible with the control location in phi, and second, we require a mapping from the concrete processes in C to the process groups in phi. And last but not least, we require that the global condition in phi is compatible with the number of processes in C. Here the number of processes in C is 3, and that the global condition is not contradicted by any of the head of multisets. Then we need to define also our entailment relation. So we say that the constraint phi1 is smaller than or equal to phi2 if, first of all, they have the same control location, and second, they have the same process groups. And last, we require that the global condition in the bigger constraint entails the global condition in the smaller constraint, which means intuitively that the bigger constraint is more restrictive or is stronger than the smaller one. In our approach, we require to compute predecessors for constraints because we start from bad constraints and calculate their predecessors and follow this approach in our analysis. So if we have a constraint phi prime and a transition, then we calculate its predecessor phi as follows. So first we need to decrease the control location by one, and then I will explain in the coming slides how we calculate the predicate GL, which is somewhat challenging. But in order to obtain the process groups in phi, we need to ensure all the commands, all the possible combination of commands that can be taken by the processes in phi prime, and then this will give us the process groups in phi. You can see that the process group in phi prime can split to several process groups by taking different commands in backward, and you see on the other hand that several guarded commands in phi prime can merge somehow to one single process group in the predecessor constraint. So for the computation of GL, we need three steps. In the first step, we need to ensure that in the predecessor constraint, the number of processes has not changed. Our assumption is that the number of processes is n, so we add an invariant for every variable saying that the sum of the number of occurrences of different values for that variable is n. Because we have one instance of these values per process, this entails that we have n processes in the predecessor. The second step is that we need to ensure that GL satisfies the guards of all the guarded commands that were taken by the process groups. So we need to conjunct our predicate with guards, and also we introduce some axioms that we call herd of axioms, or hacks for short. Hacks axioms are related to the kind of faults in the systems. For example, in the one-third rule algorithm, we have lossy communication. So for that, we add axioms saying that the number of received messages being equal to D is smaller than or equal to the total number of occurrences of D among the processes. This is because some of those might get lost. We add such axioms for any lossy communication. When we have corrupt communication, the axiom is a bit different. So we add a parameter alpha that captures the proportion of the messages that are corrupted per round, per process, and per data value. Then we add a predicate saying that the number of received messages being equal to D is smaller than or equal to the total number of messages being equal to D plus alpha, because at most alpha messages can be altered so that they have the value D. The last part in computation of GL is that we need to add axioms that relate cardinalities in phi and phi prime. So those axioms were introduced in detail in our paper, and they have two versions. The exact version is costly in terms of computation. We showed that we can over-approximate one with the axioms that I am presenting here, and this over-approximation was shown to be enough to verify interesting examples. This axiom says that if no process modifies a variable, for example x, the number of occurrences of different values for x in the predecessor and successor are the same. On the other hand, if all processes assign the same value to a variable, for example x, then the number of occurrences of that value in the predecessor is smaller than that or equal to that value in the successor. Otherwise, we just over-approximate by true. So in order to compute the global condition in the predecessor, we need to add the invariant and the guards of all the guarded commands and their axioms that capture the faults in the systems, and also we need to conjunct with the global condition in the successor and the DAX axioms that talk about the cardinalities. The red part has variables for both predecessor and successor. But we need to project away all the variables that belong to the successor. This is why we have this projection. So in our programs, we will have only finitely many invariants, finitely many guards, because the commands are finitely many, and finitely many herd of axioms. But the red part, because of its existential quantification, might produce infinitely many predicates. We want to avoid this because we want to ensure termination. So in order to overcome this issue, we over-approximate the red part by doing predicate abstraction using guards of the commands in the program. This over-approximation is first of all fully automatic. We don't require any predicates given by the user. We use the predicates in the guards. And then it makes sure that because it's a predicate abstraction, it makes sure that only finitely many GLs are produced. And our experimental results showed that this over-approximation is enough to verify interesting examples. Our verification procedure is as follows. We use a backward reachability analysis with a working list algorithm. Briefly, it works like this. We start from some bad constraints and then apply all the possible transitions in the system to them and compute the predecessors, and then repeat this process until we reach the initial state. If we reach the initial state, we report that the program is buggy and we show the trace. Otherwise, if we see that we have finished traversing the state space and couldn't reach the initial state, then we report that the program is safe. And in general, one might get lost in this process forever, but we show that we actually terminate. So we have one theorem that says the proposed procedure is sound. We have shown a sketch of its proof in the paper. This means being sound means that if the original program that we want to verify is buggy, our approach will never report that it is safe. We have also shown that our proposed procedure terminates. This is because in our analysis, we only generate finitely many constraints. Let's have a closer look to that. So a constraint is a tuple that consists of 3 parts. The control location is finite. It's a value from 0 to the number of transitions. The global condition we showed how we over-approximate to be only finitely many. The last part is the set of process groups. Each process group is represented by evaluation, and we assumed in our work that the values belong to finite domain. So we are sure that the subsets of it are, which are process groups, are also finitely many. So because we generate only finitely many constraints, we will have our approach terminate. Here are some experimental results. So we verified with our approach the one-third rule algorithm, a simpler version of that, and also another algorithm which has corruption false. One-third rule algorithm has transmission loss only. Then for each of these examples, we take into account all the safety properties for the consensus, because these all are consensus algorithms. And then for each property, we capture 2 versions, a correct version and a buggy version. For all the correct versions, our tool successfully reported that the program is safe, and for the buggy versions, it returned a valid trace. We conclude here. We have studied the subclass of algorithm inherit of model and proposed a symbolic representation using cardinality constraints on multisets to model sets of configurations. We introduced the sound and terminating procedure for checking state reachability for lossy or corrupt communication. We did our analysis for unbounded number of processes, and our approach is fully automatic, and we have checked our approach with some preliminary experiments. Thank you for your attention. This is my contact information.